So ladies and gentlemen, what I want to describe here is one of several studies that we have run which have probed the question. Might anyone be able to get me a bit of tea? Just a bit more tea. And it's super much. That probes the question, to what degree are the sort of data we gather through high-resolution phenomena luxuries or necessities? To what degree do they simply have a nicety effect in terms of, being able to probe some additional questions, but not fundamentally, they're not game changers? Or to what degree do they actually shape in a material way our answers? In a really big way, do they influence our answers? I'm talking here about high-resolution data sources, the high-velocity data sources. And we've conducted a variety of studies on this, which have been contributed to the literature, and where one of them, about to see, is about to be contributed to the literature. And that is the impacts of observation frequency, recording context, on reconstructing contact networks for epidemiological models simulation, and the degree to which that impacts spread of infection. So contact patterns of contact between individuals are of great importance in many human spheres. Thanks enormously. I'm sorry for your trouble. That's great. One of them is transmission of pathogen. That's the one we'll talk about today. But it's also extraordinarily important for transmission of norms, transmission of ideas, transmission of attitudes, knowledge, behaviors. And at the same time, contact patterns are one of those elusive elements, manifestations of human behavior that are very poorly reported by individuals. We've done studies with traditional instruments comparing with what's recorded by tools such as Ethica, and found night and day differences between what people report, say in terms of with whom they spend the most time, versus what's actually recorded on the phone. And being able to collect and analyze close proximity human contacts has been hypothesized to be important for understanding the dynamics of disease spread, going to understand patterns in the population, and to develop and improve interventions that will be effective. Now, the advent of modern measurement technologies, these Bluetooth beacons that Alex may yet demonstrate within the course of this boot camp, of smartphones and that can contribute to this discovery, has inspired a lot of close proximity data collection of great richness, and that includes the data collected by Ethica. At the same time, we put a lot of effort into collecting these data. It requires a lot of data to summarize these contact patterns, and there's a natural question: to what degree is this needed for our sphere of studies? I was talking with Andrew about this last night when it came to accelerometer data, for example. There's a lot of studies in Ethica that have reflexively recorded accelerometry in addition to step counts, for example. But there's the question, to what degree is it worth it? I mean, in many Ethica studies, accelerometry occupies 80% of the collected data is accelerometry data because it's such high resolution. Unless you have a clear idea in mind of how to use it, you might find that that's not a useful, that's not effort that's rewarded. So we'd like to know, to what degree does observation frequency, extra observation frequency, adding to observation frequency, really pay off? What's our bang for the buck in terms of recording things more frequently? To what degree does it depend on our particulars of our research area? for infectious disease, for example, the pathogen of concern? To what degree does it depend on the nature of the community being studied? How much does the model deviate from underlying situation as we'd interpret it with the finest grain data as observation frequency is scaled back as we're collecting things less and less frequently? And are there opportunities to reduce it greatly without compromising confidence in the results? And to what degree can we use synthetic network data compared to real network data? So the methodology that we employed here is we collected Bluetooth-related data from contact patterns of individuals within the study. These were consenting individuals, like all of our studies, who went through informed consent process, consented to contribute their data. We filtered it down to the study period, and we particularly focused on closer contacts, contacts that were plausibly within a few meters, I believe, of one another. And basically what we did is we examined the degree to which downsampling the data. It's kind of, you may have heard of gene knockout studies. This is data knockout studies. We actually knocked data out of the data set and asked how much, if we only sampled, given that we know data where the results when it's sampled only every 5 minutes, if we were to imagine we knock out every other data point there as if we are only recording every 10 minutes, to what degree do our conclusions differ? To what degree does it affect the model results? How if we only record it once an hour? Would we arrive at the same conclusion? Suppose we recorded it every 4 hours. How much would that distort our results compared to if we had every 5 minutes? That's the fundamental questions. For this, we used 5 different studies. These were the so-called Saskatchewan human ethology data sets, shed 1, 2, 7, 8, and 9, as collected with varying sets of participants, including, they're all basically students and staff at the U of S, sometimes related to our department, in other words, a more closely knit community, sometimes related around campus. These data sets typically ran for about a month, and they had varying numbers of participants, with the larger ones varying up in the 70s and the smaller ones having in the 30s. Now as we sampled less frequently, as we sampled more infrequently, there was longer times between frequencies. We actually saw some significant changes in the distributions associated with the number of people over time who are, in terms of the network characteristics. I'll leave it at that. And as we sort of simulated recording things less frequently, it changed the appearance of how many people are coming into contact with, between, say, 5 people, 10 people, 15 people, within a certain period of time. Now, we studied the effects of recording more frequently or less frequently on the appearance of, or on the results that the model got in terms of predictions of infection for each of these data sets for a wide variety of simulated infections. The idea is we plugged into the model the epidemiological characteristics, the parameters associated with chickenpox and diphtheria and measles and Middle Eastern respiratory symptom, the norovirus and pertussis and SARS. When we sort of parameterized the model saying, imagine the people in the study were exposed to this, that one person started with it and it would spread from there. And we simulated it with with the full data set, so with recording every 15 minutes, versus with successively reduced so-called downsampled versions that where we knocked away more and more data. It was only every hour, every 2 hours, or every 4 hours. And what you see within these results here is an indication of how this affected things. So along the x-axis, for a given infection, that's the y-axis here, for a given data set, that's the x-axis here. So the y-axis is infections, distinct infections, so everything on a given row. For example, this is H7N9. This is SARS down here. And the y-axis here is the data set. Okay, so a given column is one data set. And what we looked at was as we increased the time between observations, lowered the frequency, to what degree would that change the predictions of the model in terms of the median number of people infected? This is a result of a massive number of simulations where with a given frequency we'd simulate it again with different people initially infected, etc. And the fact that you see some variation across the x-axis of each of these graphs suggests variability. So for example, for SARS here, for this data set, the very first one here, which I believe is shed, the first of the sheds, shed 1, this first column. What you see is that as we successively increase frequency, we're getting larger and larger deviation. That's what this x-axis is. So 80% deviation is here, for example. In other words, it expected a very different number of people to get infected than were infected with the highest resolution data set. 0.4 would mean it's 40% off. As we scaled back the recording frequency successively, it'll be 40% off. Okay. So here we are scaling back the recording frequency successfully. I believe it's a power of 2, if memory serves me, and we saw the effect. What's notable here is that for some infections and some data sets, this makes a big difference. Example would be SARS for shed 1 along the x-axis, or SARS for shed, the second shed, which I believe is shed 2, although I'd have to check, yes, shed 2. And this shed as well, which may be shed 8. By contrast, for some of the sheds, it actually made comparatively little difference, which is thought-provoking. Some infections, for example, this one here, H3N9, seem to have very little difference induced by scaling back the frequency. We could measure it at a slower frequency and get very little difference. Something like norovirus up here spreads very quickly, and you see big variations if you slow it down. And that occurred across many. But the top one, chickenpox, comparatively little change compared to something like MERS or norovirus or pertussis here, but particularly MERS and norovirus. At the same time, you see for different studies, as indicated by the different data sets, as indicated by the different columns, there's very different pictures that can emerge too. For something like norovirus, this third one up, for certain of these shed data sets, scaling back didn't seem to make as big a difference. The network appeared pretty stable as you viewed it more frequently or less frequently in terms of its characteristics. Now, I haven't described what the x-axis or the y-axis is here within each graph. The y-axis indicates the degree of variability in these results as we ran it many, many times. So if it's further up on the y-axis, we would get more variable results, and this specifically relates to the interquartile range here. So we're getting some patterns of greater variability, as well as differences in accuracy. So you can think of this x-axis as kind of the accuracy difference, and the y-axis as being the difference in terms of how much is the variability when we aggregate the network, this sort of furthest one to the right, compared with the variability when we just sample every 15 minutes. Okay, so that's what that graph shows, and what it does show is that these things, that pathogen matters a lot to the results, and secondly, simulated pathogen, and second of all, the nature of the participant interactions is captured within a different data set makes a lot of difference as well. Secondly, I want to depict here the differences depicted in terms of the network structure when we measure things at different speed. Basically, this last one examined the impact on perceived infection spread. How much does the model think will infection be spread? This one is looking at how does it change the appearances of network structure. And what you can see is, once again, certain infections, as shown in this column here, say diphtheria, appear to have very different patterns of how they spread compared to a situation if we measure it every 5 minutes versus if we measure it less frequently. The diagonals along here, basically we see no difference, but as we go to more aggregated levels, we see the induced network has very different characteristics if we are aggregating it up at a very coarse level, say by measuring things every many hours, or say once a day, versus if we measure it very frequently. So in short, what this is showing is, once again, for different data sets shown on the y-axis here, and for different infections, there's variation. The same basic infection, let's say this one here, measles, when we look at it with the lens of shed 8, in shed 7 we see rather different results, shed 2. Flu, we also see somewhat different results against data sets in terms of how different the results are when we simulate it within a data set, its spread. And we were to measure things frequently or not at all, what would the implied structure be? So what we're seeing here is the effect writ large of disease characteristics and data set characteristics on the impact in terms of infection spread. So there are infections where we can scale back how frequently we measure contacts. For example, H7N9, we can scale this back. For something like pertussis and SARS, we need to measure frequently. And we can scale back for communities with lower clustering as compared to larger amounts of clustering. If we look at the university as a whole, we see real clusters because the university is broken up into individuals who are clustered, whereas departments, there's more mixing between it. And so with lower cluster coefficients, it turns out that we can scale back our frequency of recording. And simulations do require different numbers of runs in different disease and community contexts in order to draw reliable conclusions while retaining confidence in the results. So in short, disease, that's the x-axis here, and nature of the community measured as indicated by the y-axis, have a real impact on the nature, can have a real impact on the nature of results. Of when is it safe to measure things more frequent, or safe to scale back, measure things less frequently, deal with daily summaries, compared to when do we need to measure things every 15 minutes. Our other work points to the same thing. Some authors have argued that it's good enough to measure, say, a typical day of exposures, and that will be representative for most days. And our work quite clearly shows that's not the case. There's enough variation day to day that you really actually want to record many different days to get reliable conclusions. Going in and recording a typical day for a participant is just not going to be enough to get reliable results. We can't use static networks and just assume everyone is in a network whose characteristics never change, or else we'll be misled in terms of our conclusions. If we run a model assuming a static network in a model which uses a dynamically varying network, the results are very different. So does collected contact network skew as observation frequency reduces? Yes, it does. And it is affected by the nature of the community. Does the model deviate from the underlying truth as far as how far the infection spreads as we reduce frequency, as we aggregate up? We consider just the average sort of over the course of the day, how much people are interacting rather than considering every 5 minutes who they're with. Yes, it does deviate, and how much it deviates depends on the disease and the community. There are certain guidelines for when it's safe and when it's not safe to aggregate up in that way. Are there any opportunities to reduce observation frequency without compromising results? Yes, there are. And there's some rules of thumb that we've produced about the types of infections you might be studying, which would allow you to study it with lower resolution, and the nature of the communities. We can reduce the frequency with which data, but it does have implications in terms of number of runs we need to run to get consistent results out of the analysis. So that's my summary. Winchell has done this analysis, and I'm trying to summarize a quite complex and actually very long-running study, but I hope I provided some of the essential components of it. Are there any questions I could answer here with regards to this work? I think the big picture for me of this work, which reinforces the big picture for other studies we've been involved in of this sort, of which there are several, is that the types of data we've talked about this week, high velocity data in particular, is not a luxury for many needs. For many needs, if we don't have recourse to that data, our conclusions will be off, not by 10% or 5%, by 50%, 80% or more, in terms of what we conclude, in terms of the burden of in this case, infection we expect, and potentially in terms of the impact of interventions. So there's many cases, I believe, where just as for astronomy, we need a requisite level of resolution to meaningfully answer questions. We need equipment that is responsive to the level of precision we need to reliably eke out an answer, to resolve certain issues. So it is with epidemiological data collection. To this point, in epidemiology, until very recently, we've been largely blind to this fact because we haven't had recourse to collect data in a reasonable way without burden that would be so off-putting as to be infeasible for large numbers of different types of human behavior. But what the sort of studies that we've conducted seem to suggest is that this extra resolution afforded by these high resolution data sets is not merely a nicety. It's not merely a luxury to be layered on as sort of a nice feature, an innovative feature, but in some important contexts, it's a game changer in terms of what you can conclude. I argued before that that's true in terms of understanding effects across multiple pathways. But here, and in some other studies, we showed it's also true in the quantitative level of burden we expect to see coming out of certain contexts. And it should be sobering because it suggests that these tools, far from being relegated to those purely interested in innovation, may be needed more broadly to come to reliable conclusions on important health issues. Okay? So I wanted to give you a glimpse of that. This is a piece of a much larger story that involves some other studies. You will find me with some other videos online where I talk about other pieces of this. But there's some very fine work from Winchell, which helps illumine this important issue. Any questions I can answer? Yes?
The process of gathering data does affect the result?
Yeah. Yeah. The process in the sense of how frequently we get it. Are you talking about other aspects of gathering it as well, like smartphone versus maybe measurement with a wearable or something like that?
Yeah.
Could be. Here, so I can't answer that definitively. What I can tell you is here we examined the impact of frequency of measuring it. In another case, we've examined the impact of frequency of measuring and resolution spatially of measuring. And that also makes a big difference for certain types of calculations. I would imagine in terms of multiple types, ways that we might affect the data, it might affect who joins the study. It might affect the burden on the participant, which affects dropout, attrition for the study. Conceivably, it could affect people's behavior in some ways, although we hope it doesn't. Sort of a Hawthorne effect that affects how much they circulate. But I don't think that issue has been probed to my knowledge, other than kind of the resolution of the data, frequency with which we collect temporally, and spatial resolution, which we've also examined. So thanks for the question. Other questions? Okay. The energy in the room